Whether you're a beginner or a seasoned 3D artist, modifiers can assist you in sculpting, deforming, or otherwise enhancing your modeling and animation workflow non-destructively. My name is Paul Kajeji for cgcookie.com, welcoming you to Modify, your comprehensive guide to Blender's modifiers. While you can view this course as a primer on the fundamentals of modifiers, it can also be used as a guide to refer back to. Each chapter covers a specific modifier column, and each lesson is a comprehensive explainer on a single modifier. So for example, if you're stuck wondering why your curve modifier is misbehaving, Chapter 2, Lesson 3 should give you the specific information you need to troubleshoot your issue. Modifiers are typically added to an object via the Data Properties tab. However, some modifiers, such as armature, will be automatically added through other operations. Modifiers are not limited to mesh objects. They can be added to a range of other object types in Blender, including curves, text, volumes, and even grease pencil objects. The modifier list will be different depending on the types of objects you are attempting to add a modifier to. You won't find options such as Boolean or multi-resolution for text, curve, or surface objects, for example. And while grease pencil objects can have an array, mirror, or even armature modifiers added to them, most of its modifiers are entirely specific to grease pencil. While I've taken great care to include as many modifiers here, there are of course some obvious omissions. The modify column, for example, covers modifiers which are mainly situational, when you need to work with normals, UV maps, weights, and even data transfer, not the stuff you'd normally encounter when just starting out. The physics column deals with simulation, which is an area of focus that could demand its own self-contained course. And lastly, while geometry nodes does appear as a modifier under the generate column, our course Assemble covers geometry nodes in great detail. Modifiers can be stacked, rearranged, and adjusted on the fly, allowing you to model procedurally or automate repetitive effects without having to keyframe or write complicated Python scripts, saving you valuable time. So whether you're sculpting characters, modeling architecture, or just want some procedural effects in your scene, modifiers will help you accomplish your tasks quickly, easily, and dynamically. With our default cube selected, let's go over to our Modifier Properties tab and select Array from the drop-down list. I'll swing into front view so we can see this more clearly. The Array modifier has three modes under Fit type. They are Fixed Count, Fit Length, and Fit Curve. There are three offset modes you can choose from: Relative, Constant, and Object. By default, Relative Offset is selected, so let's focus on this for now. We've got three factors by which we can offset an instance. Currently, the X factor, or the amount by which the new instance is offset in the X direction, is set to 1. This will be clearer in wireframe mode. You can see that the default cube is 2 units or 2 meters wide in the X direction. It is repeated once, and the instance is placed directly adjacent to the original cube. You'll notice that the default count is set to 2. This includes the original object in that count. Increasing the count places each instance adjacent to the last, according to the offset mode and its factor. Relative offset means that the factor is in reference to the object's dimensions. To demonstrate, I'll toggle into edit mode. If I increase the width of this object along the x-axis, each instance is moved along so that it still sits adjacent to the original object. The cube is now 3 units wide. The factor x has remained at 1. I'll return the cube to 2 units in width. Now let's enable the constant offset and examine the options. The offset options for constant are measured by distance, in this case meters. Meters is the default unit for Blender. Because the cube is 2 meters wide in the x dimension, but the default offset is only set to 1 meter, each instance now overlaps the previous one. Let's increase the distance x to 2. Now we have something similar to what the relative offset did automatically. Let's increase it again to 4. Each instance is placed 4 meters from the center of the previous instance. If we increase or decrease the width of the object in the x direction, the instance's placement doesn't change. Finally, let's look at object offset. As the name suggests, we require an object to tell the modifier how to array the instances. I'll add a plain axes empty. By default, the axes only stretch 1 meter in each direction, which means it will fit neatly inside this cube. Let's modify that, so that when we are in solid shading mode, we can still see it and select it. We'll reselect the cube so we can see its array modifier settings again. We can use the eyedropper tool in the object selection box to select the empty. Nothing seems to have changed yet, even though our count for the object array is still set at 5. We'll select the empty and move it in the x direction. As we move the empty, you'll notice that the duplicate instances now become visible. The instance adjacent to the original object is locked to the empty, and each instance after that will be placed at a relative interval. Let's see what happens when we rotate the empty around the y-axis 30 degrees. You can now see that each instance's rotation is set relative to the last instance. This also works with scale. I'm going to scale the empty down to 50% or 0.5. Notice how each instance is now scaled 50% of the scale of the previous instance, and not the original object. Here, we have a cylindrical object with a relative offset factor set to 1 in the z direction. Editing the object will offset the instances according to the object's own dimensions. Remember, relative counts the object's dimension in the offset factor we're applying as 1 unit. If we set the factor to more than 1, then gaps will begin to appear. Let's enable the merge function. The default is set quite low, as it assumes instances will automatically be close. Let's increase the distance to 0.35. This tells the modifier that any vertices between instances that fall inside a 0.35 radius should be merged. There's another setting for merge, which will look for first and last copies in an array which forms a ring. Here is a segment of a torus set to object offset. I'll enable the merge function, as well as the first and last copies setting. The object around which we're offsetting is an empty, and it is placed at the same location as the object's own pivot point. The edges of this torus segment are rotated 20 degrees around the z-axis from each other. So rotating the empty 20 degrees should position the duplicate so that the first vertices of the duplicate align with the last vertices of the original mesh. We can now dial up the count, and each instance will be set exactly 20 degrees in front of the last until we complete this ring. Incidentally, I chose 20 degrees because 20 times 18 will give us exactly 360 degrees. But because this object is not smooth, no change to the object is detectable. So let's add a subsurface modifier to the stack, and now when we disable the merge function in our array, you can clearly see how even though the object and its instances are smoothed out, every junction is noticeable. If we leave the merge function on, but disable first and last copies, now you can clearly see where the first and last copies meet, as these edges are not merged. Texture will also be something to consider when creating instances of an object using the array modifier. I've set up a generated UV grid, unwrapped this plane, and created a shader in which this grid acts as a texture. You can see the mapping node tree below in the viewport here. Opening the UV settings under Array, we can offset the U and V coordinates of this texture. Now I've set the UV grid texture in the shader node tree to UDIM tiles so that each instance won't be repeated and leaves behind the familiar node texture purpley pink color. The offset U is set to 0.05 units. The offset is added to each instance along the array. And this also happens when offsetting the texture in the V direction. The caps setting allows you to cap an array with some objects. The orientation and object center is an important thing to note, as there are no controls in the array modifier to adjust the result. So let's have a look at where we need to be mindful of these properties for array caps. I've created 3 separate meshes: a pillar segment, a base, and a top. I've added an empty at the same coordinate as the pillar segment. This will act as the object offset for this mesh. I'll go ahead and add the array modifier to the pillar. I'll disable the relative offset and enable object offset, and set the object offset to empty. I'll now move the empty so that it sits in line with the top of the pillar mesh, and I will scale it proportionally so that the bottom of the first instance matches the top of the original object. I'll enable merge and now open up the cap settings. I'll select the base as the cap start object and the top as the cap end object. If we swing into front view, we'll immediately see the problem that the cap start object has. It does not sit where we expect it to, because the offset of the cap is calculated from the cap object's own origin, then offset by however far the object is moved. In order to get the base to sit correctly, we'll need to select the base, tab into edit mode, and move the mesh away from its origin by the same amount of units as we've moved the object we're using to offset the array. Now that I've correctly set up the base, let's go one step further. I'll rotate the empty 10 degrees around the y-axis. This will cause gaps to appear on one side of the pillar. So I'll enable merge and increase the factor of merge until the gaps are automatically filled. Now we've got an interesting model, all using one modifier. With the default cube selected, go to the Modify Properties tab, click Add Modifier, and select Bevel from the Generate list. You can immediately see the effects of the modifier. Let's toggle into Edit mode and show edges. The default setting is edges, but you can also set the modifier to bevel vertices. There are several options for width type, and each calculates the bevel a little differently. To get a clear idea of how each type functions, let's toggle into wireframe mode and disable the modifier in viewport shading. We'll mark out where the original edge exists. Now, when we re-enable the modifier for viewport rendering, we can see in front view how the bevel has been applied. In offset mode, the amount is measured from the original edge back along the direction of the adjacent face. If we switch the type to width, the bevel is measured between the two new edges formed. Switching to depth, the amount is measured from the original edge to the newly beveled face. Absolute is similar to offset, calculating the bevel a set unit away from the original edge. Finally, percentage will calculate the bevel as a percentage of the adjacent face length. In this example, 5% happens to be the equivalent percentage to the offset amount. 0.1 of a metre is 5% of 2 metres. The bevel modifier has a number of limit methods to calculate what is beveled and what isn't. The default setting is angle. The specific angle in question is measured between the face normals of adjacent faces. If you want to see this clearly, let's tab into Edit View and enable face normals in Viewport Overlays. I'll move this edge over. Now if we project the face normals until they meet at an angle, we can measure that angle and see it's about 59 degrees. In our bevel modifier, if we set this angle to 59, any angle above 59 degrees will be beveled, and any angle below it will be ignored. You can set a number of segments which curve the bevel between the newly created edges. The higher the segment number, the smoother the bevel. The profile for the bevel is set to super ellipse by default. This can be modified between a maximum and a minimum value, which correspond to the position of the original edge and the point where the edge is beveled. We'll change the limit method to weight. We'll have to assign a weight value to specific edges that we want bevel. I'll toggle into edit mode, select an edge, and using Ctrl E to bring up my edge specials menu, I'll set the edge weight to 1. Now, only this edge will be affected by the bevel modifier. Let's change our bevel profile from super ellipse to custom. Instead of a factor, we now get a curve, which shows the profile of our bevel. Let's use one of the presets available to us. If we select support loops, the custom profile will be created using the number of segments and width type that we have already selected in the bevel modifier to draw out the curve. If we change any of the above parameters, the custom profile won't be dynamically updated. We'll need to reapply the preset to make the new profile. Sampling straight edges and even lengths are two settings which calculate the average of the bevel between the new edges. But in cases where the segment count is low, these settings will approximate the bevel based on the profile. The more segments you have, the more accurate your profile will be. Now let's take a look at miters. There are two types. An inner miter will be formed along a concave edge, whereas an outer miter will be formed along a convex edge. Under the geometry setting, each miter has various modes for calculating how the bevels are smoothed out. The outer miter can be set to sharp, patch, or arc. By comparison, the inner miter only has two settings, sharp and arc. Increasing the spread of the miter will affect inner and outer miters. Let's reset our limit method to none. Intersections where three or more edges meet at a single vertex can be set to bevel at one of two modes. Grid fill, in which the corner will be beveled with a smoothed grid in accordance with all previous settings, or cutoff, in which the bevel creates a face which will meet an intersecting beveled edge depending on that vertex's normal direction. The bevel modifier also has some neat fixes which are enabled by default for when things inevitably go haywire. These are best shown by disabling them on the kinds of objects where these situations may arise. This Susan monkey head has the bevel modifier added to it. If I disable the clamp overlap, the width of the bevel is disregarded. Enabling it accounts for surrounding topology and will scale down the effects appropriately. Loop slide is important in special cases where you have n-gons formed by a Boolean function. Here I have a cube with a Boolean modifier set to difference, and the modifier is targeting this smaller rectangular shape so that a window is formed. I'll now add the bevel modifier on top of the Boolean. Loop slide is enabled by default. If I select the Boolean object and move it around, you can see how the bevel around this window scales proportionally. But if we disable this, then the bevel around the window remains equal, regardless of where the Boolean shape is positioned. Under shading, we have a few different settings which correct for different situations. I've added the bevel modifier to this headphones object. Now, if the shading on the object is set to either flat or smooth, this is usually a default. When you enable harden normals, you'll get this warning message telling you to enable auto smooth in object data properties first. So let's go ahead and do that. Here is one place where you can find the setting. Hardening normals won't change the topology, but rather how the lighting interacts with the affected faces. By matching the normal direction of adjacent faces, problematic shading is corrected. Marking seams and sharp edges corrects problems that might occur when you finally apply the modifier. Let's mark some sharp edges and some seams. In Viewport Display, I'll make sure we can see these when we enter edit mode. I'll duplicate the object, and on the original, I'll leave the marks disabled. Selecting the duplicate, I'll now mark seams and sharp. Let's now apply the bevel to both objects. If we shift select both and toggle into edit mode, we can spot the difference. When the modifier is applied, the generated sharp and seam marks are corrected for. This could lead to some undesired shading or UV unwrapping situations down the line. The material index will allow you to assign a material to only the beveled edges. Let's add a second material, and let's tinker with the settings. Finally, there's the face strength settings. This is definitely one with a few surprises. On its own, you're not going to notice any perceivable change between the face strength settings. But if we add a modifier which requires face normal data, let's say weighted normal for example, then the face strength settings come into play. Now we can better see how altering the weight of the normals will affect how the surface reflects in scene lighting. You'll see here that the bevel modifier is higher in the stack than the weighted normals modifier. So when we alter the face strength settings, the bevel can set the influence on whether none, new, affected, or all faces are influenced by modifiers which depend on face normal data lower down in the stack. I like to think of Booleans a little like Venn diagrams, but in 3D space. Here we have two objects, and here is where they cross over. I'll add a Boolean modifier to the object on the right. The default operand type is set to object, so I'll select the blue circle as the object that will create the Boolean. There are three modes you can set the modifier to. They are intersect, union, and difference. Let's rotate into 3D space, where you can see that these circles are actually cylinders. The blue cylinder is still visible here, even though the Boolean operation is set to difference. We'll hide the blue cylinder. Because the blue cylinder is positioned higher than the yellow cylinder, you can see how its form cuts out a piece of the yellow cylinder more clearly. If we set this to intersect, you can see how the shape is defined by the borders of each object. In edit mode, the original cylinder can also be seen. When switching to union, there'll be a little bit of Z fighting between the object that has been selected as the operand and the sum of the meshes. So let's make that invisible to see what is going on. You'll immediately notice that the compound mesh has inherited the material of the original object. Now, because the shading is set to X-ray, you can also see how the topology is redrawn around where the objects intersect. I'll make the blue cylinder visible again. Moving the object around, you can also see that the modifier updates dynamically. I'm going to add the Boolean modifier to this smoothed out cube object, but this time, instead of using an object as the operand type, I'll select collection. I've set up a pre-made collection of spheres called dots. This will cut out the dots on each side of the die when the Boolean is set to difference. I'll hide the cube for the moment and unhide the dots collection. See how each of the spheres is a separate object. There are two options for solvers. Index-based is the default. We've already seen how this results in transferring the material of the original object to the Boolean operation. I'll set the viewport to rendered view so we can see this difference in action. The dots have a different material. I'll hide the dots collection once more and switch the solver option material setting to transfer. Now, whatever is cut out of the original object will use the material of the object or collection of objects. There are two solver settings. So far, we've only seen how it works when set to exact. I'll show you an instance when the setting fast comes in handy. Here, I have this n-gon shape. It's a cookie. You can see this clearly in edit mode. It is not solid, it's just a two-dimensional object with a single face. I have a collection called cutouts, and this has three solid closed objects, which we will use as the Boolean operand. They have been positioned to intersect through the cookie object. I'll hide the collection once more, and I'll add a Boolean modifier to the cookie. I'll change the operand from object to collection, selecting cutouts as the collection. Now nothing seems to have happened, and this is because of the main difference between the two solver algorithms. The two solvers work in slightly different ways. Fast is obviously the simpler of the two. It uses an overlap threshold based on the distance between the overlapping meshes to calculate what should be included in the operation and what shouldn't. Exact will take slightly longer. And if we have an object that has some other modifiers already added to it, it's perhaps the better option, because the geometry that is calculated before a Boolean is even applied might have some unexpected overlapping, self-intersecting, or some holes might have appeared that you were previously not aware of. Let's take this cylinder as an example. It has a solidify modifier on it, and we'll add a Boolean modifier, set it to difference, and use the object I've called holes punch to create the Boolean. If I set the solver to fast, it seems to do an okay job. But now let's adjust the hole punch object. At some point, the Boolean does not perform well. In fact, it can get things completely wrong. And altering the threshold won't solve these errors. If we switch the solver to exact, we seem to have an issue with the Boolean around this part of the mesh. But our options have changed so that we can now account for self-overlap and even holes. Now if we rotate or move the holes punch object, the viewport does lag a little since the exact solver takes more time, but we don't get any of those errors or artifacting as we did before. Sometimes, however, exact will not give you the desired effect, and fast will actually give you a better solution. One final note on the exact solver. Only when the operand type is set to object will you get both self-intersection and hole tolerant options. If the operand type is set to collection, you'll only have the hole tolerant option available. The build modifier is an animation effect which builds a mesh on face by face. The order in which the faces appear are based on their index. If you want to see this, here's how. Let's open our preferences and under Interface, tick Developer Extras. Back in our viewport, we'll tab into Edit mode and go into Face Select mode. Under my viewport overlays, there is now an additional item, Developer Indices. This will overlay the index assigned to any face, edge, or vertex selected. Let's select this Susan monkey head. Let's add modifier and select Build. By default, the mesh seems to have vanished, but if we scrub forward in our timeline, we can see how it builds on over the default 100 frames starting at frame 1. If we tick the reverse box, the mesh begins in its completed state and the faces are subtracted instead. You can control which start frame the build effect will begin on. Let's set it to 50 frames. The length controls the number of frames that the mesh will build up over. Let's also set this to 50. Now, the mesh will remain hidden until the animation hits frame 50, and then it will build up over the next 50 frames. Enabling Randomize will build or hide the faces in a random order. You can also alter the random seed to get some variation. I'll select this sphere and add the decimate modifier. Each mode has a different way of reducing the amount of detail on a mesh. By default, the mode is set to collapse and the ratio is set to 1. The ratio is a proportion of the number of faces that remain. As we reduce that ratio, the faces are merged by collapsing the nearest edges. If we enable the symmetry setting, we can mirror the modifier's effects along the X, the Y, or the Z axis. By checking the box next to triangulate, each n-gon with 4 edges or more is split and collapsed into triangles. Let's select a more complex mesh, such as this statue, and add the decimate modifier. You can isolate the modifier to a specific vertex group. However, you can alter the factor by which the vertex group is affected by the modifier in relation to the other groups. If we reduce that factor to 0, the modifier will affect all the other vertex groups. Now let's change the mode from collapse to unsubdivide. As we increase the iterations by which the modifier will unsubdivide the mesh, you can notice how it affects the overall vertex, edge, and face count. It is generally a good idea to enable the statistics in your overlay settings, but as a guide, the modifier will track the face count directly, updating it depending on the number of iterations you are unsubdividing by. Finally, there is the planar option. This will calculate a number of n-gon planes depending on the angle limit that we set. If we increase the angle limit, less planes are generated to approximate the original mesh. This is especially apparent when increasing the angle limit to something quite high. The delimit settings are various ways you can tell the modifier what borders to ignore between areas of the mesh. For example, we could tell it to ignore planes which meet at a predefined seam. As we increase the angle limit, the seams we marked are ignored. And here I've marked some sharp edges around the disk. By holding down Shift, you can deselect the delimit factor. Checking the box next to all boundaries will take into account all of the above boundaries and generally create more n-gons than planes.
Edge split effectively splits the continuity between faces in order to achieve a sharp edge along a subdivided or smoother surface.
Demonstrating how the edge split modifier works is best done on a complex model such as this orbot.
I'll enable statistics in my viewport overlays so we can better see how splitting edges will in fact increase edge and vertex counts. I'll tab into edit mode, select an edge, bring up my edge contextual menu and select edge split. The edge and vertex counts have gone up slightly, and if I reselect this edge and move it, you can see how it's split off. I'll undo this and add the modifier to replicate what we just did in a non-destructive way. I'll increase the angle, and as I do, you can see how the edge and vertex counts increase dramatically as the modifier searches for edges which satisfy this threshold.
If your object is set to flat shading, let's change this to smooth shading. By default, the edge angle is set to 30 degrees, and this is activated, as is the sharp edges setting. Let's disable the settings for the moment so we can have a closer look. I'll toggle into edit mode so we can clearly see that some of the edges have been marked sharp. These can be highlighted or even isolated in your overlay settings. The way you mark an edge as sharp is fairly simple. When we're in edit mode, you can select an edge or hold down Shift
and Alt and select an edge loop. You can select several edges or edge loops this way.
Once we've selected a few, we'll bring up our Edge Specials menu by hitting Ctrl E. And from this menu, we can select Mark Sharp. Now let's re-enable the Sharp Edges setting in our Edge Split modifier to see the result. I'll deselect it and just enable Edge Angle. The default is set to 30 degrees, which means any faces which meet at an angle greater than 30 degrees are treated as a sharp edge.
Enabling face normals is a good way to see what angle faces meet at. Here is a simple plane. I've split it down the middle, so now we have two faces. I'll tab into Edit mode, and in our viewport overlays, I'll enable Face Normals and Edge Angles. I'm going to set my cursor to the center edge of this plane, and I'm going to set my pivot so that any rotation occurs around the cursor. I'll now select this outer edge and rotate it around the y-axis so that the two faces are now set at an angle. The inner angle is 120 degrees, but the edge angle that is measured is showing us that these two front edges form a 60-degree angle. But here is where Blender measures this angle from. And it's a little counterintuitive. So here's a way that makes more sense to us end users. Let's increase the size of the face normals until they intersect. Now in front view, I'm going to use my measurement tool to draw out this angle. I'm going to click on the origin points of where the normals are emerging. Then, holding down Control, I can click anywhere between these points on the measuring line and drag that point to where the face normals meet. You can now clearly see that the angle formed between these faces is 60 degrees. I'll tab back into Object mode, and I'm going to set the shading for this plane to Smooth. If we set our edge angle to 59 degrees, then we see that the angle here is drawn as sharp. The edge is split. But if we set our edge angle to 61 degrees, then this angle is drawn as smooth, because the threshold for what is considered sharp and what isn't has been exceeded. Now, the usual way we use this modifier is to combine an angle and sharp edge setting. Sometimes the angle will suffice, and you can dial the angle to whatever gives you the best result. But if some edges are outside of that boundary, marking them sharp and enabling sharp edges will give you the result that you're after. I'll add the mask modifier to this default cube.
Like some other modifiers, the effects are not immediately apparent. I have assigned a number of vertex groups to help demonstrate what the mask modifier does, and you can see these groups here in wireframe view. Let's toggle back into solid view, and with the cube selected, we'll take a look at the modifier properties. The default mode is vertex group, so under the vertex group dropdown, I'll select bottom. Now the mask modifier masks out anything that isn't assigned to the bottom vertex group. I'll enable viewing in edit mode for this modifier and tab into edit mode so we can see the other vertices. Let's increase the threshold. As it approaches 1, nothing seems to happen, but when we hit 1, then the bottom disappears altogether because this group is also now masked. If we enable the smooth function, everything except the furthest face appears, and now when we slide the threshold factor, it will smoothly transition from no mask to full mask. If we invert the vertex group selection, we can do this in reverse. Let's deselect the inversion and set our threshold to 0.5. And now let's select a different vertex group. The same effect is applied, but now it treats that vertex group as the point of origin. When we toggle to armature mode, the settings are a little bit different. Instead of a vertex group, we can select an armature to use as the mask. I'll select the armature we see here as the target. And immediately we'll see these parts of the cylinder masked out. Let's take a closer look at the cylindrical object. There are a couple of vertex group which correspond to the armature's bones, and even though we won't be using these groups in the mask, they're necessary for the armature to deform the mesh. The lower group corresponds to the lower bone, and the upper group corresponds to the upper bone. As with most rigging situations, there is an overlap to assure smooth deformation. Let's go back to the modifier properties and toggle back into object mode. In order to see how the mask affects the mesh, we need to select the armature and toggle into pose mode. Because the upper bone was already selected, the mask modifier is showing all the vertices associated with that bone. Let's select the lower bone. Now this doesn't update in real time, so we must tab out of pose mode, and when we do, the mask is updated to only show the vertices associated with the lower bone. I'll go back into object mode, reselect the cylinder, and increase the threshold. You'll note that there is no smooth function in this setting, but because our cylinder has more edge rings, and because the overlap of each bone group is strongest at the extremes, raising the mask threshold will hide each edge ring incrementally towards the part of the group which has 100% weight assigned to that bone. And just like the vertex group mode, we can invert the armature selection. The mirror modifier is applied to half a symmetrical mesh for the purposes of sculpting or modelling. Here, I have the right half of a Susan monkey head, and when we add the mirror modifier to it, it seems to restore the opposite side. By default, the axis along which it mirrors the mesh is set to X. You can set this axis by which the mesh is mirrored to either X, Y, or Z. Let's see this more clearly. I'll go into top view, disable the X-axis in the mirror modifier, and in edit mode, I'll rotate the mesh around in the Z-axis so that it is aligned along the Y-axis. Now, when we enable Y, the mirror will replace the missing half along the Y-axis. To get it to mirror correctly along the Z-axis, let's do the same, but this time rotate it around the Y. We'll now enable the Z-axis for the mirror. You can also apply the mirror modifier to a full object. There is a bisect function, which allows you to also split away half the mesh in any axis. With the axis and bisect both set to X, I'll tab into edit mode and I'll select some vertices. Now you can see that the left side is modified as if it had been applied to an already bisected mesh. If we disable the bisect, we now get an overlap with the original mesh because it is still present. Bisecting Susan along the Y-axis, one side of the object is mirrored. When we flip across the same axis, you can now see the opposite part of the mesh is mirrored. I'll mirror and bisect along the Z-axis. I'll tab into edit mode and move the mesh up along the Z-axis. Mirroring along an axis will flip the vertices across wherever the object center happens to be. I'll return our axis and bisect settings to X and take a look at the mirror object settings. I have an empty already in the scene, so I will eyedropper select it. I've made it deliberately larger so it can be selected more easily. Back in front view, and with the empty selected, You can now see that the plane of the mirror lines up with wherever the object is moved to, but because our axis and bisect are locked to X, only its X position is taken into account. All the other axis positions are ignored. I'll disable X axis and enable the Z axes for both. Let's move this empty up a little and rotate it. Moving the empty along its local axis, I can affect how the mesh is mirrored. Let's now go back to a traditionally bisected mesh mirrored along the X-axis. In edit mode, we'll move the mesh along the X-axis so a clear gap appears between the two halves. With clipping disabled, the mesh will pass through the plane and mirror on the opposite side were it to be moved along the X-axis. But with clipping enabled, the same action causes the vertices to collapse along the mirror plane. The mirror modifier also has some options to take into account UV information. I've projected from view this mapped grid onto the Susan monkey head. Tabbing into edit mode, you can see how the mesh is projected onto the grid over in the UV editor. If I mirror along the X-axis, the grid flips over the entire mesh. But if I enable bisect on the same axis, you can see how the right side of the grid is mirrored on the left. And if I flip across X, the left side is what is mirrored. Let's make things a little bit clearer. I'll draw the axes that correspond to the U and V directions on the mapped image. Both axis and bisect have been enabled, so we can clearly see that the right side of the UV map has been mirrored across to the left side of Suzanne. Now, under Data, let's enable Mirror U. Because the UV map is mirrored, it now adopts the left side of the UV map. We can also shift this mapping of the mirrored side along the U axis. Let's imagine we're mapping a full image across a mesh on which we've applied the mirror modifier. Already we see the right side is mirrored automatically onto the left. Now let's enable Mirror U under Data. I'll tab into edit mode to make this more obvious. You can see that only half the mesh has a UV unwrap, but the UV data is what is mirrored here, so the left side of the image is now what is mapped onto the mirrored side of the mesh. We'll select this low poly head and add the multi-resolution modifier to it. There are 3 levels you can view multi-res at: Viewport, Sculpt, and Render. By default, no levels have been added, so you cannot toggle to higher levels of subdivision just yet. I'll turn off optimal display for the moment and add a few subdivisions by clicking the Subdivide button here. We are now able to dial back the viewport subdivisions to anything below 3, the maximum we've currently set. I'll set each subdivision level to a different setting so we can see when the difference becomes relevant to a sculpting workflow. I'll toggle into camera view and re-enable optimal display. This overlays the original low polygon wireframe over the subdivision surface. You'll be able to faintly see the subdivided faces. Let's disable it once more so we can see each level clearly. I'll toggle into sculpt mode now. You'll notice how the resolution is subdivided at a higher count than when we were in object mode. Now I'll bring up a render in which I composited the denser wireframe so you can see how the render setting is even higher again. Back in viewport, I'm going to set my sculpt setting to 3 and toggle back into sculpt mode. We won't go too deep into sculpt settings, but it is important to point out a few things while we're here. For example, I've set the mirror function to X and I've set the sculpt draw radius to 50. Now when I draw on the surface, the mesh will be deformed on both sides of the X-axis. If we toggle back into object mode, because the viewport level is still set to 1, the deformation will also be shown, but with reduced resolution. By disabling the viewport preview, you can see that the original mesh can still be seen without any sculpting done to it. This is because, by default, the sculpt base mesh is not enabled. I'll enable it now and sculpt another area of the mesh. I'll disable the viewport preview once more, and you'll see that these areas have affected the base mesh, whereas the previous areas have not. If you set all your subdivisions lower and hit delete higher, this gets rid of anything above the subdivision you just set. There are a couple of options for subdividing higher resolutions of a base mesh. You'll notice that there's a few options for adding a resolution of subdivision. There's the main subdivide button, but there are two smaller buttons below it, simple and linear. You can think of the main subdivide button as using the standard Catmull-Clark subdivision algorithm. Both simple and linear are much like the simple subdivision method, in which you can add extra topology but not necessarily smooth the edges. They are, however, slightly different. To illustrate how, I've got this basic cube with a multi-resolution modifier added to it, and I've given it one level of subdivision. I'll duplicate this cube a couple of times, and on the first duplicate, I'll add a simple level of subdivision, and on the second duplicate, I'll use linear. You can immediately see the difference. Applying simple or linear as a first level of subdivision and adding a further subdivision on top of this will create a slightly different result, as that subdivision is working on the extra topology that has just been generated. If we were to apply this modifier to the mesh, we could still restore the levels of subdivision in reverse by reapplying the multi-res modifier and then using the unsubdivide button. I can hit the unsubdivide button for each level we wished to restore, but you have to note that you cannot restore more levels than were previously available. There's also an option to transfer the sculpted information from one mesh to another. On the left, I have a head mesh that has some sculpting done to it after a multi-res modifier was added. And on the right, we have a head mesh with only the multi-res modifier added, but no sculpting done. I'll select the left head, then shift select the unsculpted head on the right. I can now hit the reshape key, and all of the sculpting detail is transferred. If I select the head on the right and hit apply base, this will deform the base mesh to fit the higher resolution sculpt. You can see that the head on the right has not had any sculpting applied to its base mesh. It is sometimes handy to save sculpt information externally to the blend file that you're working in. This can save a lot of hassle, especially if your file will take a long time to load. This base mesh has not been modified, and the sculpt is only present when the modifier is viewable. I'll click on Save External under the Generate section. This will open a Save dialog box, and I can save this sculpt data in an exterior file, which this mesh will reference. I can also return that data to the blend file by clicking on Pack External. Let's select this high-resolution mesh and add the Remesh modifier to it. It will default to the voxel option, but let's start by looking at the blocks setting. The first setting under blocks is the octree depth. An octree is a structure for partitioning spatial data in 3 dimensions, in which each iteration increases by a factor of 8. A grid is generated based on the octree depth and the longest dimension of the mesh, in this case, its height. The depth is set very low to begin with, So the approximation of this statue appears as a handful of large cubes inside the volume of the original mesh. As we increase this number, it will represent the mesh in higher resolutions, and the cubes appear to get smaller because the ratio between this statue's height and the resolution of the ever-increasing density of the grid decreases each time by a factor of 8. You can also reduce the scale of this factor, which results in larger blocks. I'll reset this to its default. Remove disconnected simply means any part of the mesh which falls outside of the threshold set will not be included in the final result. Let's reduce that threshold now to demonstrate. As we approach 0, the disconnected piece will now be included once the ratio is small enough. And finally, there is a smooth shading option. For those of you wondering why there is, it is because this tool can be used to quickly retopologize a mesh in preparation for sculpting. Speaking of smooth, let's look at the next option along. Smooth has all the same controls as blocks, but instead of generating a grid of cubes, it will retopologize the mesh to the closest approximation of quad geometry based on the octree depth, scale, and threshold. Increasing the octree depth will result in a denser mesh, but overall you lose definition due to the smoothing out of sharp edges. The next setting is sharp. This setting will take into account areas such as we see here along the hairline, where angles between faces shouldn't be smoothed out. Sharp has all the same controls as the previous two options, but also has a control for sharpness. A higher setting will create an effect closer to the original mesh, and lower settings will be less accurate. Finally, we have the option to recalculate the mesh using voxels. The density is measured in scale units instead of ratios. The smaller the voxel size, the denser the result. So if you wish to retopologize for a lower vertex count, it's a good idea to increase the voxel size. The adaptivity will calculate less topology where the surface is smoothest, and denser topology where it is more detailed. This option will create poles and triangles as the mesh transitions between areas of varying detail. Let's apply the screw modifier to this circle mesh filled with a single n-gon. By default, the axis is set to Z. The angle is set to 360 degrees. The screw offset is set to 0, and the iterations are set to 1. I'll explain what each of these mean in turn, but let's begin with the axis. As you can see, our circle is now a sphere. I'll make the geometry wireframe visible using our overlays, so we can better see what is going on here. Here is the z-axis, and the circle has been rotated around it 360 degrees once. If we change the axis to x, you can see how the mesh is rotated in a different axis. Now watch what happens when the circle, which is oriented in the xz plane facing out in the y direction, is rotated around the y-axis. It is no longer a sphere, but some kind of weird ring. If we go into edit mode, and we rotate all the vertices 90 degrees around the z-axis, then it becomes more apparent, and the circle is once again a sphere, with its poles aligned along the y-axis. I'll reset the axis to x, and drop the angle to 90 degrees. Because this is a full circle, and its object origin is at the center of that circle, the entire object will create these 2/4 of the full sphere. I'll increase the iteration count to 2. Now we appear to have a full sphere, But what's really going on is that each 90-degree rotation is being repeated twice. I've reduced the angle to 0 degrees and the iteration count back to 1. I'll tab into edit mode and move all the points back 2 meters in the Y direction so that the object origin remains in the same place. I'll set the angle back to 90 degrees. Let's set the screw value to 2 meters. Note that this setting is affected by the axis that is chosen, so the circle is extruded and moved 2 meters in the X direction. Now if we increase the iterations, it will repeat this shape by the number of degrees. If you alter the screw distance, you can create a thread with greater or less frequency. You can also use an object as the axis point. I'll add a cube here, and I'll reduce its size in edit mode so that its object scale remains at 1. I'll select our circle once again, and I'll use the eyedropper tool next to the axis object field, and I'll select the cube. I had disabled the display in viewport setting so that this process was clearer, but now I'll re-enable it. Now we can control the radius of the effect by moving the cube. You'll notice, however, that the radius is only affected in any axis which isn't currently selected. I'll now enable Object Screw. This will disable the screw by distance setting, as the position of the axis object now overrides this function. Whichever axis we move the object along, the modifier will affect how the screw is applied. By default, the object is repeated over 16 steps. There's a viewport count and a render count. Just like with other modifiers, this refers to the number that is previewed in the 3D viewport and at render time. Let's reduce the count to 8, but increase the angle to 180 degrees. You'll notice that the count is now spread over the total shape, even though the degree count is higher. In this example, we're going to look at what the merge function does. Let's take this single edge. Now the object origin is set in line along the x-axis to what will be the point of this cone. I'll set the angle to 90 degrees and the iterations to 4. Let's leave the merge function disabled for the moment and take a look at the cone's apex. There are 12 vertices here because the steps are set to 12. Let's apply the modifier and go into edit mode. If we select a point on the apex, you'll see that this point is not attached to other points, even though they occupy the same space. It hasn't automatically merged them. I'll undo the last couple of steps, and this time I'll enable the merge function. Now when I apply the modifier, it will automatically merge these points, as they are well within the designated threshold. UV information can be applied to the modified mesh. Let's take our circle example. I'll add the screw modifier to it, set its rotation to 90 degrees around the x-axis. And to demonstrate how a material is applied, I have generated this color UV grid and plugged it into the base color input of the default principled BSDF shader. My viewport is set to material preview, so when I apply this material to our object, we can immediately see how it is mapped onto its surface. Let's take a look at the modified properties once again. The stretch UV setting allows us to stretch the U and V coordinates across the surface of the generated mesh. If we increase the iterations and increase the screw distance, then continue to add iterations, you'll see how the image is repeated for every iteration. This would be of great use for tileable textures, for example. Lastly, we have some options for correcting any normals issues. By default, smooth shading is enabled, and disabling this will switch the object to flat shading. To see what the next two options do, I'll enable face orientation in my viewport displays. If for some reason your normals are incorrect somewhere along the surface, calculate order should correct any issues. In this case, it will simply reverse our normals since everything is pretty consistent. And finally, you can flip the normal direction altogether. The skin modifier will generate polygonal mesh around single vertices or edges with no face data. I'll start very simply and add a single vertex. The option to do this is hidden in an add-on which isn't enabled automatically. If you go to your preferences and we go to our add-ons, we can search under Add Mesh and enable Extra Objects. This will allow you to add, among a lot of other things, a single vertex. I'll now add the skin modifier to it. Starting simple gives us a good idea of some of the things skin does by default. It creates a quad mesh 0.25 units around the vertex in each axis. I'm going to go to my display settings and toggle wireframe mode on, and I'll also enable X-ray. I'll make sure that in the skin modifier, I can view the changes while I'm in edit mode. Let's extrude the vertex up 1 meter in the Z direction. I'll select the original vertex and I'll extrude it again in the X and the Y direction, so now we have a simple branch. By default, Symmetry X is enabled. I'm going to disable this for the moment so we can look at branch smoothing. By increasing this setting, the topology around any vertex which meets at 3 or more edges will be relaxed. The symmetry attempts to fix any problematic areas around these vertices by addressing the quads which sit across the X, Y, or Z axes. With or without branch smoothing on, these usually make cleaner topology. Smooth shading simply creates the same kind of smooth shading you get when assigning any mesh a smooth shade. We'll circle back to create armature in a moment, but first let's look at the mark loose and clear loose settings. By default, the skin modifier will calculate the most optimal amount of edge rings between two vertices. But if I mark this root vertex as loose, then no edge rings will be generated between the vertices. However, if I subdivide an edge ring will now appear around the new vertex. I can also clear loose vertices so that the edge loops will be generated evenly along any edges. You may have noticed this red dotted line around one vertex in particular. Depending on the order in which you may have extruded out branching vertices, this might not be sitting at the original vertex. You can select any vertex you wish and mark it as root. Doing this impacts the kind of armature that is created when we click on the Create Armature button. I'll duplicate this mesh, and along with it its modifier, and I'll mark two different roots. You can only see the root vertex in edit mode. Now, I'll create an armature for each. The default display for the new armatures is stick. But to see what's really going on, it's better if we switch this display to octahedron for each of them. I'm going to also enable Show Names. The armature on the left only has 3 bones. It begins where we marked the vertex's root and extends down, then branches out along the X and the Y arms. However, the armature on the left is a little different. It consists of 4 bones. An extra root bone has been generated from which the 3 arms branch out of. Any vertex marked root which connects 2 or more edges will have a root bone created in this way. I'll focus on this right mesh for the moment. I'll select it and take a look at the modifier properties. You'll notice that an armature modifier has automatically been added with the object armature selected, preserve volume and vertex groups enabled. under the object data properties, even though 4 bones were generated for this armature, only 3 vertex groups have been created. Let's take a look at the armature and toggle into pose mode. The mesh has automatically been set up with this custom armature, basic weight painting, and a hierarchy. This means if we grab the root bone, this should move the entire armature. Not shown in the modifier, but a handy tip to know, is how the radius of the generated mesh can be scaled and modified around any vertex by hitting Ctrl A. This is the equivalent to scaling vertices on a mesh using Alt S to shrink or fatten geometry. You can even constrain the scale of the X, Y, or Z axis after you hit Ctrl A by hitting the corresponding key. If you wish to remove any asymmetrical scaling, you can use the Equalize Radii button.
I'm going to add the Solidify modifier to this two-dimensional mesh. Even in its default setting, you will immediately see how it adds depth to this cookie logo. There are 2 modes, simple and complex. We'll focus on the simple mode for the time being. The thickness setting dictates the amount of thickness that is added. It is measured in real-world units, and since my default Blender units are meters, I will set this to 0.005 or 5 millimeters. The direction in which the thickness is applied is in relation to the face normals. The original mesh is sitting at the world origin, and because the default offset is -1, the solidify effect is applied in the negative direction to the face normals. Setting the offset to 0, the solidify effect is evenly distributed in the positive and negative normal direction. And setting it to 1, the solidify effect is applied in the positive orientation in relation to the face normals. I'll set this back to 0 for the rest of the demonstration. The even thickness setting will adjust your mesh when it encounters sharp corners. Sometimes the modifier doesn't approximate the desired effect, and this cookie has a couple of sharp edges such as this, which could benefit from enabling this setting. By default, the rim setting Fill is activated. If we deactivate this setting, you can see that the rim between the original faces and the newly created parallel face vanishes. By adjusting the thickness, you can see that this affects the distance between the original face and the parallel face. Let's bring the rim back and enable Only Rim. Now from this angle, it looks like nothing appears to have changed. But if we flip to the other side of the object, you'll see that there is no parallel face that is generated. Here I have duplicated the mesh and assigned 2 vertex groups. Group 1 is the cookie on the left. Group 2 is the cookie on the right. We can assign the Solidify modifier to a specific group. In this case, let's assign it to Group 1. You'll also notice that there is a factor setting, and by increasing this, you can incrementally apply the modifier to anything that is not assigned to Group 1. You can also apply the modifier to the inverse selection of the vertex group. To demonstrate how the modifier can be affected by the direction of the face normals, let's take a look at this shallow cylinder. We'll enable the face normals in our overlays so we can see what direction they are pointing. Simply enabling flip won't show these reversing in edit mode. I'll disable the setting, go back to object mode, and activate Only Rim. You'll notice that the parallel faces now have disappeared. If we flip the normals,
you'll see how the opposite faces vanish. Let's now take a look at the material settings. The first is the material offset, which dictates the material assigned to the parallel faces. When everything is set to 0, these faces will simply adopt the original material of the object. Let's disable the rim for the moment and go into rendered mode. Let's take a look at my material settings. Here you'll see that I've already assigned 3 materials to this object: orange, black, and white. The orange material at the top of the stack is what is currently shown. Let's go back to our modifier properties and change the material offset from 0 to 1. You'll now see that the parallel faces have adopted the second color in our material stack. I'll assign an offset of 2 for the parallel faces. And now if we re-enable the rim, we can assign a material to offset just the rim separately. In this example, we'll take a brief look at the edge data settings. I've added solidify to this plane. I've also added a subdivision surface modifier after solidify. Let's increase the thickness to 1 meter. I'll remain in edit mode, but I'll make sure we can see the modifier changes while we're in edit mode. However, I will keep the on cage setting disabled so we can see the original plane. If we increase the inner crease slider, you'll see this affects the parallel faces, flattening them out, thereby overriding any subdivision that the next modifier will apply. Setting the outer crease to 1 will do the same for the original faces. And increasing the rim edge data will make the subdivision modifier redundant, as all edges now appear to have an edge crease of 100%, and this will override any data which could be smoothed out by the subdivision surface modifier. Bevel Convex looks for bevel weight data you might have added to edges or vertices, and can adjust how the weight is distributed for modifiers that rely on bevel weight data lower in the stack. I've added some bevel weight to this edge here. I'll add the solidify modifier to this mesh. I'll enable even thickness, and I'll give it some extra thickness so that we can see this effect more clearly. Now I'll add a bevel modifier after our solidify modifier and set the limit method to weight. I'll give this about 6 segments. You can see how the bevel is transferred to the inside wall of this solidified mesh. Moving the bevel convex setting in the negative direction will reduce the inner wall's bevel until it is no longer apparent. Moving the bevel convex in the positive direction will be able to control how much bevel is added to the non-weighted edges and vertices until the entire exterior solidified mesh behaves as if everything has a bevel weight of 1. Note, however, that the inner wall will only display the bevel on the edge that the bevel weight is applied to. The thickness clamp will help prevent you from creating intersecting geometry. An example where this could happen would be something like this simple bowl. I'll add the solidify modifier to it, and I'll increase the thickness quite dramatically. I'll enable X-ray so that you can see that the resulting geometry actually intersects in the narrower section of this bowl. This means that if we were to apply the modifier now, the resulting geometry would require some cleanup. So instead, let's use the thickness clamp to solve our problem before we even get to that step. We can increase this clamp to a soft upper limit of 2, although if you require, you can push it beyond by typing in a larger value. The clamp will examine the distance between the outer and inner walls, so if the resulting geometry is smaller,
it will create a thinner wall. Enabling angle clamp changes the clamping method from the distance between outer and inner walls to the angles between faces. On this open cylinder shape, I'm going to go to its data properties and create two vertex groups. I'll call one shell and the other rim, but I won't assign any vertices to them. In my solidify modifier, under output vertex groups, I'm going to add the shell group to the shell section and the rim group to rim. Now I'll apply the modifier. When I tab back into edit mode and take a look at my cylinder's data properties, the vertices that were generated as the shell and the rim have now been applied to the corresponding vertex groups. If you apply and you discover that the wall is incorrectly attributed, undo a couple of steps, flip the normals, and reapply. The simple mode works great for most cases. But when you have meshes which show non-manifold topology, angled or scaled extrusions, or even holes, then you're probably going to want to use the complex mode. Here is a model to which, when I add solidify to it, it will immediately show problematic areas. We could try to adjust a few things. Perhaps set the offset to 0, try and enable even thickness, and even adjust the thickness to a level which is the least problematic, but we will still not produce an optimal result. Switching over to complex, you'll notice a couple of differences. First off, the even mode is no longer an option, but what we have is a thickness mode and boundary setting. The thickness mode has three settings. Fixed is the simplest, and if we compare it to the simple setting, we see that it performs slightly better on thickening the walls of this mesh. Even will produce a much nicer result. And constraints might seem like it makes this area, for example, worse, but when we look at boundaries and how to set these correctly, you can see where constraints comes in handy. To understand boundaries a little bit more clearly, let's take a look at these three open cubes, which I've duplicated with Alt-D, so editing one will edit all of them. I've added a solidify modifier to each of these, but I've set each to a different boundary mode. As I edit this open boundary, you can see how each reacts a little differently, hinting at some uses you might encounter. None is fine for a mesh which is simple and even, but if, however, you have areas in your mesh where you want the walls to have proportionally even thickness, round is a good setting. And if you wish those boundary areas to be angled as if they've been planed, then flat is the best option. Back to our complex model, with the thickness mode set to even and our boundaries set to round, looks passable. And setting our boundary to flat, the back curved wall shows some serious artifacting. Now let's set our mode to constraint. This corrects any problems with the curved wall. All the other settings will adjust your mesh as with the simple mode. Using all of these settings in conjunction, you should be able to tackle and correct for most situations. To better see what the subdivision modifier actually does, I'm going to enable wireframe in my viewport display. This will make it more obvious to see what is going on. I'll select the Susan monkey head, go to Add Modifier, and select the Subdivision Surface modifier from the list. The mesh smooths out, but because we're still in flat shading mode, you can already see the subdivisions between the original wireframe. Let's take a look at the modifier and explore some of the settings. There are two subdivision modes, Catmull-Clark and Simple. You can also set
different subdivision levels for your viewport display and at render time. These can be increased or decreased independently of each other. By default, optimal display is enabled. If I untick this, all the subdivision levels will now appear in wireframe. If we switch over to simple mode, the subdivisions are now stretched across the existing faces, but the mesh retains its original shape. I'll switch back to Catmull-Clark. As with most other modifiers, you can enable or disable when the modifier can be displayed. I can view the modifier applied at render time, in the viewport, and when in edit mode. The on-cage setting is disabled right now. I'll tab into edit mode, and you'll see that the modifier is applied, but the original mesh appears as a cage around the object. Let's enable the on-cage mode. Now the edit mesh fits to the final result. The on-cage setting can resemble the optimal display. This object is still flat shaded. I'm going to switch this to smooth, and now we can see how this modifier can really help with the final result. The original mesh will now act as a cage, and as we move vertices around, the subdivided mesh will dynamically update, almost as if there was a proportional fall-off applied. There are some advanced settings which, by default, are enabled to give the most optimal results, and they can be adjusted for more specific uses should you need them. Use limit surface, for example, is ticked by default. The limit surface is what the Catmull-Clark algorithm would draw if subdivision was assumed to be infinite. Let's disable this setting to see what the classic Catmull-Clark subdivision does. You can see that each subdivision is approximated based on the average distance of the existing points. Each level of subdivision will repeat the process until you reach this theoretical limit. So you need to have quite a high subdivision count to approximate that smoothing. Enabling use limit surface, however, the generated vertices will be drawn towards this theoretical limit, giving you a more accurate result with less subdivision. You can also increase or decrease the quality when using the use limit surface method. This will further refine the approximation, and on a subdivided cube, for example, it's most noticeable around areas where the vertex is furthest from the limit surface, such as the cube's corners. Here I have a simple mesh. I've already unwrapped and added a material to this mesh. I'll enter Material Preview mode, and I'll add the Subdivision Surface modifier. Under the Advanced settings, we can use the UV Smooth to address where the UV map is stretched. It's set to keep boundaries by default, but I have set it to none, so that you can see how badly the unaffected mapping is at first. I've marked out what areas of this mesh are defined as boundaries, junctions, corners, and concave areas. As we select the various settings, you can see how each of these areas are corrected, eliminating the stretching of the UV map. The boundary smooth option is set to all by default, as this will smooth out all the mesh's topology. A boundary is an open edge. A corner is only where two edges meet. That's why when we set boundary smooth to keep corners, only these areas are kept sharp. But these areas are not, because we have extra edges meeting the vertex here. You might have marked some creases on your mesh. These are areas where you can apply heavier sharpness to where faces meet. The subdivision modifier can take these areas into account. To illustrate what a custom normal is, I'm going to add this normal edit modifier and move it up in the stack, and I'm going to set the target to this empty here. I'll set this modifier to directional, and I'll enable face orientation in our viewport overlays so that when we move the target around, we can see which direction the normals are facing. But if we enable custom normals, this will better correct for any normal customization. Let's select this Susan monkey head and add the triangulate modifier to it. It has two settings for detecting and splitting existing faces into tris, quad, and n-gon. Given that it creates three-sided faces, the minimum cannot be set to less than 4. You'll note that all the faces by default have already been triangulated, so raising the minimum vertex count higher than what any existing faces currently have will disregard those faces. Notice since most, if not all, the faces on this mesh are quads, setting the minimum vertices to 5 or higher will result in no triangulation at all. Let's go through some of the settings for each available triangulation method. We'll switch the quad method to fix. What this does is draw a diagonal across the quad from the first to the third indexed vertex of each face. I'll mark the vertices here with the grease pencil. If we counted clockwise around this quad, then the quad is split from vert 1 to 3. We'll switch to fixed alternate, and this just splits the quad from verts 2 to 4. The next two settings simply calculate the shortest and longest diagonal and split the quad across these diagonals respectively. The n-gon method calculates tris in one of two ways: beauty and ear clipping, when looking at a mesh which is subdivided after triangulation. Beauty attempts to make tris that look the best visually, while clip uses an algorithm that's simpler and faster to calculate. The volume to mesh modifier shows up in the modifier menu when selecting a mesh object. However, the mesh to volume modifier only shows up if you have a volume object to select. In order to best explain what the volume to mesh modifier does, let's first take a look at the mesh to volume modifier. I have here a very high resolution scan of a clay dragon. I've added a sun lamp to the scene, and I've given this dragon a principled volume shader. The mesh to volume modifier can only be applied to a volume object, so let's add one. I'll hit Shift A to bring up my add menu. I'll select a volume and then select empty. While this empty object is still selected, let's go to our modifier properties. Only modifiers which can be applied to a volume will show up here. We'll select the mesh to volume modifier. Under the settings, we'll need to select an object to create the volume, but so that we can see this effect more easily, I'll make sure that the dragon will be hidden when it's rendered, and in its object properties, under viewport display, we'll set the display as for this dragon to bounds. This is handy since it will show you the boundary inside which the volume will be constrained, but it will not show the dragon mesh. I'll select the volume object from the outliner. I'll eyedropper select the dragon's bounding box. It might take a second, especially if the object is extremely high resolution, like this one, but you'll see the volume has now taken on the shape of the object. I'm using the Cycles render engine for this particular demonstration. Let's toggle into render display. Now I'll have to hide the dragon object in this mode, but you can see more clearly how the light I've set up in this scene interacts with the volume. Let's take a look at some of the settings we have available to us, which will help further adjust this volumetric shape. First, we can adjust its density. naturally the higher we set this factor, the more opaque the volume becomes. If we untick Fill Volume, you can see how the voxels are distributed inside the volume of the mesh. You can think of a voxel like a cubic space, in much the same way a pixel occupies a square, but in 3 dimensions. Before we re-enable the Fill Volume option, note the 2 settings below it, exterior and interior bandwidth. Currently, both these settings are active. The exterior controls how far the gradient will extend outside the mesh, or in this case, the voxel. The interior controls how far inside the gradient will extend. If we enable the Fill Volume once more, only the exterior bandwidth is active. We have 2 resolution modes. Voxel Amount counts the number of voxels generated along a single axis of the overall volume. The higher we set this, the smaller the voxels are. The effect appears as though the mesh is more faithfully represented because the resolution is higher. Voxel size works in reverse. It will calculate the size of the voxel first, then will fill the space according to how many voxel it needs to fit along that axis. So now let's see how this can work in reverse, or by using the volume to mesh modifier. We can apply this modifier to any mesh, so we may as well stick with the default cube. In our modifier properties, we'll add the volume to mesh modifier. The settings appear similar to the mesh to volume modifier, and the cube appears to be hidden. This is because it requires a volume to reference in order for this to work. This time, I'll add an OpenVDB file from the drop-down menu. An OpenVDB file is something that holds volumetric simulation data and can only be imported into Blender in this way. The axis of an OpenVDB file is usually Y up, and the scale might be quite large, so rotating and scaling the volume might be necessary. However, we saw with using the previous modifier, any translation, rotation, or scaling will be reflected in the resulting mesh. I'll set the viewport display for the volume to bounds, and I'll disable it in render view, so that this object remains hidden at render time, but is still selectable in solid shading mode. Now with the cube selected, we can use this object as the volume to reference. A generated mesh will appear, taking on the approximate form of the volume. For this modifier, there are 3 resolution modes: grid, voxel amount, and voxel size. The grid name is imported from the VDB file. It usually references the base grid that is already packed into the VDB file, which in this case stores density values. When the resolution mode is set to grid, it will use this imported base grid distribution of voxels in order to generate the resulting mesh. The voxels can vary in size according to the density, hence why this mesh can appear to have finer details in some parts. The threshold refers to the size of the voxels which will be included or excluded from the volume. Decreasing the threshold will allow finer detail present in the base grid to be included. If we increase this threshold, less and less voxels make the cut, until no voxels are left to generate a mesh. Results can be quite dense at low thresholds, so you can slide the adaptivity from 0 to 1 in order to reduce geometry in places where it's not needed. You can also enable smooth shading should you require it. The other 2 resolution settings are voxel amount and voxel size, and they work in much the same way as they did in the mesh to volume modifier we saw earlier. The amount refers to the number of voxels that will be generated along an axis, and the size refers to the generated voxels dimension. The less voxels that are present in a voxel amount, the lower the mesh resolution will appear, and inversely, the smaller the voxel size, the higher the resulting resolution appears. In both cases, the threshold and adaptivity work in the same way as they did for the grid resolution, by increasing or reducing the number of voxels permitted in the volume, and by reducing the amount of topology generated when it is not required.
I'll add the weld modifier to this Susan monkey head mesh. The weld modifier is fairly straightforward to use. You can set it to all or connected modes. You can set the distance inside of which the modifier will detect vertices to weld together, and you can even isolate the modifier to a specific vertex group. I've pre-assigned 2 vertex groups to this mesh. These meshes are already separate even though they are joined together as a single Susan monkey head. With the mode set to all, let's dial up the distance. You'll immediately see how the edges collapse, and that the eyes and head are treated as the same consistent mesh. If I switch the mode to connected, the head and the eyes will still be collapsed, but only vertices which are connected to the same mesh will be affected. Therefore, the head vertices will be welded independently of each eye mesh. I've separated out an edge loop here to demonstrate an extra setting which becomes active in connected mode. Enabling this will only collapse loose edges. These are any edges not attached to a face. Notice when it is enabled, the Susan head no longer displays the weld effect, but I can dial back the distance and affect the separated edge ring. I'll disable this once more and select the eye vertex group from the drop-down here. I can now isolate the weld modifier to just this vertex group, or just the head vertex group. I can even invert the vertex group selection. What this does is apply the modifier to anything outside of the selected vertex group. Let's select this headphones object and add the wireframe modifier to it. Now sometimes, depending on the scale of the object, the default settings can go a little haywire. I'll reduce the thickness to 0.001 of a meter or 1 millimeter. This definitely has an impact, but there are still some places where the mesh is behaving badly. I'll return the thickness to its original setting, and under the thickness section here, I'll enable relative. Now you'll see that the wireframe is quite fine, so I may have to thicken up the original thickness. Let's bump that up to 0.1 of a meter. Let's zoom right in and see what this modifier does to the mesh. You'll see that it not only deletes all the faces, but it also gives the remaining edges thickness. By default, they will adopt any material which is already UV mapped onto the object. Also, by default, the even thickness is enabled. Enabling the even thickness makes the thickness along each edge uniform. If we disable the even thickness, then the thickness is scaled along each edge depending on its proximity to other vertices, so you'll get a slight tapering in places. The modifier will replace the original geometry with a wireframe cage. Disabling this setting, however, the wireframe is now added to the original geometry. Let's go down to the material properties. Each part of this object has a material corresponding to the specific part of the headphone. I've added an extra material at the bottom of the stack. I've called this one wire, and it's simply an emission shader with its color set to white. If we return to the modifier properties and change the material offset, we can replace the default material, which the wireframe is inheriting, with the wire material.
Now that the wireframe is much more visible over the original mesh, you can more clearly see the difference that the even thickness setting makes. Let's now take a look at the offset. By default, it is set to 0. If we look closely at the headphones, we'll see what is going on when we alter this. I'll slide the offset to 1, and you'll see how the wireframe appears clearer and thicker even. But if I slide it to -1, it seems to disappear entirely. Now, when you see this in action, you can tell what is going on. It is offsetting the position of the wire's thickness relative to the original surface of the mesh. I'll reset this back to 0. Now let's take a look at the vertex group settings. As with other modifiers with this setting, this will allow us to isolate the modifier to a specific assigned group, and the factor will allow us to blend in the modifier to any groups outside of that selection. The armature modifier will automatically be added to a mesh when you parent that mesh to an existing armature. I'm going to set my armature deform with automatic weights, and the armature modifier is automatically added in my modifier properties. Toggling into weight paint mode, you can see how the weight is distributed, with a fall-off for each bone. If we take a look at the object data properties, we'll see that 2 vertex groups based on the armature bone names have been added. By selecting each from the group menu, the weight distribution is shown over the mesh. Let's toggle back into object mode and select the armature. I'm going to pose one of the bones by rotating it slightly. I'll tab back into object mode, select the mesh, and take a look at our modifier properties. The object has been automatically set to the armature we parented the mesh to. Under vertex group, we can isolate the modifier to work on just one vertex group, or the inverse, that is, all the other vertex groups, excluding this one. Armatures are going to distort meshes, sometimes in ways which might not be correct. The preserve volume setting, for example, will reduce the pinching around a joint, as seen here. By default, the armature binding is set to vertex groups, but we can switch this to use the bone envelopes instead. In object mode, I'll select the armature, and in its armature properties, I'll switch the viewport display to envelope. I'll now tab into edit mode, and we can see the envelopes reaching out around the bone. By hitting Alt-S, I can scale these envelopes to have a greater influence over the mesh. I'll tab back into object mode, select the cylinder once more, and in its modifier properties, I'll deselect vertex groups and select bone envelopes instead. You can immediately see the difference in the effect because this ignores the weight distributions assigned to the vertex groups and uses the envelope's own fall-off instead. Using the preserve volume setting will create different results. The multi-modifier option works best when there are more modifiers in the stack. For example, I'll duplicate the modifier we already have, and I'll set the first modifier to just work on the vertex group named bone. I'll set the preserve volume and bone envelope settings for this one. In the second modifier in the stack, I'll select multi-modifier and set the bind to vertex groups. Both modifiers are overlapping, causing some problems, but when the multi-modifier is enabled, the combination is corrected to give a more favorable result. I'll add the cast modifier to this low poly head mesh. This modifier shifts a mesh towards 3 preset shapes: a sphere, a cylinder, or a cuboid. By default, the shape is positioned at the same origin point as the mesh. Seeing that the head is well above the origin point, you can see how the sphere only seems to deform the bottom part of the head. Let's tab into edit mode, and I'll make sure that the cast modifier will allow us to see the changes while editing. So I'll enable the edit and cage settings in the modifier. I'll select all the vertices, then hitting G and Z, I'll move the mesh down towards its origin point. You can sort of make out the sphere around which this shape deforms. To make this clearer, I'll add a sphere object and I'll set its viewport shading to wire and set its viewport display in front. As I move the object around again in edit mode, we can get a better idea of what's going on. By default, the modifier will cast the mesh out in all three axes, but we can constrain this effect to 2 or 1. The factor is set to 0.5 by default. Now, this is midway between 0, which will have no effect, and 1, which will show the shape that the mesh is deforming towards. Pushing the factor beyond 1 or below 0 can cause some interesting or unintended effects. This is because the transition is mapped along a linear gradient, and therefore it will extrapolate the position of each vertex and will push it further along that curve. The radius will give us a boundary to which the effect can be limited to. Any part of the mesh which extends beyond this radius will not be deformed. The size will determine how far away from the origin point the effect will project. If you combine this with the radius, you can get some odd results. So if you require something smoother, try enabling the size from radius setting. Now, the radius will dictate this factor, and the result between the original mesh and the cast shape is smoothed out. The size is completely disregarded. You can, of course, assign this modifier to a single vertex group, or invert the selection, and only those vertices will be affected. Finally, you can use an object to adjust the center from which the shape is cast. I'll select the sphere which I used to demonstrate the boundary earlier, and moving that around, you can achieve the inverse of having to move the object's own vertices in relation to its point of origin. Note the Use Transform option. If this is disabled, the rotation and scale is ignored and only the object's position affects the cast. I'll now enable Use Transform, and I'll switch the cast shape to a cuboid so we can better see how this works. Now, I can use the object's scale and rotation in the effect as well. The curve modifier will deform an object along a curve or path in a chosen directional axis. It is a modifier which works best in combination with other modifiers, as we'll see in the lesson that follows. With this modifier in particular, it's important to be mindful of the orientation and position of objects and the curve which will affect the deformation. To help us along, having the gizmo visible is a good idea. If this isn't enabled, you can use Control backtick to toggle it on, or click on the Show Gizmos button here on the header. I've created this chevron object which points along the global x-axis in the positive direction. I'll add a NURBS path. Now, just so things are clearer, I'm going to edit this path slightly. I'll tab into edit mode and adjust it so that its first point sits at the origin of its geometry. I'll also scale this out along the x-axis slightly so it won't become obscured by the chevron. Now, to prevent things from going awry, it's a very good idea to parent the object to this curve. Now, I recommend to only use the simple object parenting option from your drop-down list, as other options which look for constraints or animate along paths will cause problems. Now, when we move the curve, or scale it, or rotate it, the object will follow it correctly. Let's select the chevron, and I'll add the curve modifier to it from the deform list. It has very basic options, the first being the curve object that you can select to affect its deformation. So let's do that now. I'll eyedropper select the NURBS path in viewport. We'll leave the deform axis as X for the time being because everything is pretty much oriented in the X positive direction. But you can set the deform axis to both positive and negative directions for either X, Y, or Z. Like a lot of other modifiers, you can also isolate this effect to a specific vertex group, or omit that vertex group by inverting the selection. But we won't be doing this step for this lesson. Now I'll select the NURBS path and tab into edit mode, and I'll edit the points to create an interesting curve shape. I'll select the chevron, hit G to grab, and X to constrain its movement only along the X-axis. As I move it, it will now follow and deform along the curve. Note that freely moving the chevron is going to cause some problems if it is translated along any other axis. Let's now add an array modifier to the chevron. And I'll place this array modifier above the curve in the modifier stack. I'll increase the count, and you'll see how each instance is placed along the path. Now with those basics out of the way, let's do something a little bit more complex. I've modeled a small segment of phone cable using a circle primitive offset from its origin and with a screw modifier on it that I've set to an angle of 360 degrees and set the screw offset to 0.3 meters. I've set the axis to offset along Y. I'm going to increase the iteration count to about 60 so that we've got plenty of cable to work with. I've also added a Bezier curve and modified it to a desired path that I wish this phone cable to follow. Let's now parent the cable object to the curve and add the curve modifier to it. We'll select the Bezier as the curve, but because the cable is oriented in the Y direction and the default curve modifier is still set to X, you can see how it points off in a weird direction. So let's now switch that axis from X to Y. Now the cable follows the curve correctly. Because the screw modifier is first in the stack, any adjustments to its settings will be applied first. And if we edit this Bezier curve, the cable will follow its path. Also, because the object is parented to this curve, moving, scaling, or rotating the curve in object mode will not cause issues with the mesh's own deformations. Here I have a sphere, which has a subdivision surface modifier added to it, so that we can have enough topology to see the displace modifier in action. If we need more detail at any time, this will allow us to increase topology quickly, or dial it back should our machines begin to lag. Let's add the displace modifier to the sphere. The sphere appears to grow slightly as we have not yet assigned a texture to affect the displacement of the mesh. Currently, only the mid-level setting is affecting the displacement. We'll click on New, and to the right of this texture bar setting, we can shortcut to our texture properties. Here, let's assign a procedural texture. I'm going to set a distort noise texture, and I'll adjust a few of the parameters. Immediately you'll see how our sphere has been affected by the modifier. Let's go back to our modifier properties. Some of the controls that were grayed out earlier are now active. The coordinates dictate which system the texture will displace the surface of the mesh. Local means that the texture moves, scales, and rotates along with the object. The global coordinate system means that if we move the object, it actually moves through the texture which exists in a three-dimensional cloud. If we change the coordinate system to object, then we can select an object which can move the origin of the texture. I'll assign this empty as that object. Now when I move, rotate, and scale the empty, it's almost as if what was happening with the global coordinate system is happening in reverse. UV will use the UV unwrap on the object as the system to control the displacement. We can change the mapping in edit mode, so we'll enable viewing in edit and cage modes so we can see the modifier working. Then we'll select all the vertices. I'll hit U and change the UV projection map to a different setting. Let's set the coordinates back to local. So far, the only direction we have seen the surface of the object displaced along is face normals. We can displace the object in the X, Y, or Z axis. The direction of this axis can be defined by local or global coordinates for each axis. If the object was rotated in an arbitrary direction, local would lock the displacement along the object's own x-axis, and global would override this, constraining the displacement to the global x-axis. To properly see how RGB to XYZ could work, I'll change the texture to something with RGB values. The displacement will be adjusted accordingly, where R equals X, G equals Y, and B equals Z. We'll set this back to normal and take a look at the strength and mid-level settings. Let's set our displace modifier to be visible in edit but not in cage. And in front view, we can see the original mesh as a cage around the displaced object. Mid-level is set to 0.500 or 50%. The original mesh's surface is this midpoint. If we alter this, the midpoint changes value. Setting strength to 0 means that no displacement occurs. The strength can be set to positive or negative values, and surface vertices will be displaced according to the direction set. You can also isolate the effect to a specific vertex group, or invert the effect to omit that vertex group and just affect all others. While all modifiers can be added via the Modifier Properties panel, some are automatically added through other processes. We saw this previously with the armature modifier, for instance. I'll select the default cube, tab into edit mode, and select a single vertex. You can go to the vertex menu, find hook, and select hook to new object. Or you can access the hook contextual menu by hitting Ctrl H when in edit mode. Either way, this will create a new empty and automatically add a hook modifier that is correctly set up for you. Let's add a Suzanne and an empty to act as our hook. Now let's add the hook modifier to the Suzanne monkey head. Then select the empty to act as the object hook. When doing it in this way, it won't work right away because there are a few options for assigning parts of this mesh to the form with the selected hook. One way, of course, is using vertex groups. I'll make a quick one now and assign some vertices to it. Tabbing back into object mode and looking back at the hook modifier settings, we can now select this group. And when we move the empty, these are the vertices that will be affected. we can reduce the strength by which the modifier affects these vertices. Let's open up the fall-off settings. Here we can select the type of fall-off curve we might want to use, and increase or decrease the radius over which this curve will work. I'll remove this vertex group and tab into edit mode. When in edit mode, under strength, 4 new buttons appear. I'll select a few vertices and then click on assign. This will assign the selection to the hook. Now when we move the empty, only those will be affected, much like a vertex group. However, we can reselect vertices at any time and adjust the selection without having to unassign anything. Resetting will cancel the transform, but it won't reset the position of the empty controlling the hook. Recenter will place the hook to wherever the cursor happens to be. We have to note, however, that the empty controls the hook, but isn't the actual hook. The hook is actually this point. The dotted line is much what we would see when we parent objects together. For every hook that you wish to add, another instance of the hook modifier must also be used. Some modifiers are best used in conjunction with other modifiers. For example, the hook modifier, which we saw in an earlier lesson, can make it very easy to deform meshes by assigning hooks along key edge loops. I can then select all of the edge loops that the hooks are assigned to and create a single group from all of those vertices. If I look at my modifier properties, you can see that each individual hook has been added to this stack as a modifier. If I move any of these hooks around, the vertices assigned to each will move, but the transition between the hooks will not be smooth as we would expect. I'll now add a Laplacian deform modifier to the bottom of the stack. Firstly, we have to assign a group, and so I'm going to select the group that I have already assigned all of the hook vertices to. Without moving any of the hooks first, I can now click on this bind button. And now when I move each hook, you can see how the transition between each of those hooks is smoothed out. Increasing the repeat count will give you a better result by preserving the details in the deformed mesh more accurately. But a higher repeat count will consume more resources before the smooth is calculated. To add the lattice modifier, we first need a lattice to deform the targeted mesh. I'll hit Shift-A and select Lattice. The default lattice is a cube with an X, Y, and Z dimension of 1 meter, with a U, V, and W resolution of 2. While I'm in object mode, I'll scale up the lattice to fit our Suzanne monkey head. Let's select the object, add the lattice modifier to it from the deform list of modifiers, then eyedropper select the lattice. Nothing has yet happened because no changes have been made to the lattice, so let's do that now. Let's select the lattice, tab into edit mode. I'll stretch it out, and in the lattice object data properties panel, I'll increase the lattice resolution, and I'll move some of the points around. The object deforms inside the boundaries of the original lattice. Let's reselect the object and take a look at the modifier settings. There's basically just 2 options you can modify. The strength dictates how much deformation is applied, 0 being none and 1 being 100% of the lattice deformation. Vertex groups allows you to choose a group of vertices or their inverse to apply this modifier to. Mesh deform can work much like the lattice modifier, but instead of using a lattice, it can use another object as its cage. There are some settings which we've covered in other modifiers. For example, you can add this effect to the entire mesh, a single vertex group, or inversely, omit that single vertex group from being affected by hitting the inverse button. The precision will determine how accurate the deformation will be. The higher the number, the more precise the deformation. The dynamic setting comes into play when there are modifiers or even shape keys that are added to the object. Once you've set up everything you need, you hit the bind button, and this activates the modifier using all the above settings, and you're ready to start editing the cage object. It's important to note this modifier is entirely dependent on the order in which it appears in the modifier stack. In general, you will want to have this higher in your modifier stack, as any modifiers placed above it will cause the modifier to unbind when their parameters are changed, and a lot of your work could be wasted. I have here a Susan monkey head and a sphere which will act as the mesh cage. I've set the viewport of this sphere to wireframe only, so that we can better see the effects. The Suzanne object has got a subdivision modifier added to it. I'll add the mesh deform modifier, and I'll select our sphere as the target object. And now I'll put both of these objects into a collection, and I'm going to call this collection Stack 1. I'll now duplicate the collection in my outliner and rename this Stack 2. I'll select all the objects inside Stack 2 and move them over so we can do a little bit of spot the difference. Note that automatically the duplicate Suzanne should have the duplicate sphere set as its deform object. In the Stack 2 Suzanne, let's place the subdivision modifier after the mesh deform. I'll select the original Suzanne from Stack 1. Now I'll click the bind button and all the settings become grayed out. We can now select the first sphere, tab into edit mode, and as we modify this sphere, the Susan monkey head inside it reacts accordingly. I'll select the Stack 1 Susan monkey head. As soon as I adjust any of its parameters, the mesh deform modifier becomes unbound, and the Susan monkey head reverts to its original shape. It's not a simple case of just hitting the bind button again. What this is actually telling Blender to do is to now bind this Susan monkey head to the object that's already been edited. It will not take any of the edits that we've already made into account. In comparison, let's select the second Susan monkey head, and I'll do a similar thing. Here, we see that the subdivision modifier is placed below the mesh deform. We can tinker with these settings, and the mesh deform is still bound. There's a couple of things to note here. One method isn't inherently better than another. There will be times when you want to place a subdivision modifier before a mesh deform, because this gives you a more accurate deformation, as the mesh deform will take into account all the new topology generated by the subdivision. In our Stack 2 example, the only topology the mesh deform modifier is working on is the original low poly mesh. I'm going to add a wave modifier to each of these spheres. They'll rotate around the y-axis 360 degrees over 250 frames. On the Stack 1 Susan monkey head, I'm going to enable dynamic, but I won't enable dynamic on the Stack 2 Susan monkey head. I'll click bind for both, and then play the animation. They appear similar, but let's stop right here on this frame. Here is where you can see how dynamic will give you a more accurate calculation when using an animated mesh to deform your object. The shrink wrap modifier has got a lot of settings which can be used in several combinations for different situations. Let's start simple. Here I have a plane and a sphere which I wish to wrap this plane to. I'm going to set the sphere's viewport rendering to wire so we can better see the effect it has on the plane. Currently, this plane is not modified in any way. It still only has 4 vertices to wrap to the surface of the sphere. I'll add the shrink wrap modifier to the plane. Under target, I'm going to set the sphere as the object the plane will wrap to. Now we can see how the plane seems to intersect with the sphere. Its 4 vertices have snapped to the surface, but because this one face is the only topology available, the single face appears to be inside the sphere. If I tab into edit mode and subdivide the plane a couple of times, you can now see how the newly created vertices also move to the surface of the sphere. There are 4 wrap methods, and by default, nearest surface point is selected. And it does exactly what we've just seen. It binds the mesh vertices to the nearest point on the target object. Before we take a look at the other wrap methods, let's take a look at the snap modes. Most of the settings below are shared by the wrap methods. The snap modes change how the vertices are positioned in relation to the target object. On surface is selected by default. This means if we move, rotate, or scale the mesh, the vertices are always pulled towards the nearest point on the target object's surface. If the sphere's topology is increased, say with a subdivision surface modifier, then the object vertices have a more accurate surface to snap to. Let's switch the snap mode to inside and move the plane along the z-axis. As the plane begins to intersect with the sphere, vertices inside the boundary of the sphere will revert to their original shape, whereas vertices outside will be pulled towards the surface. Outside flips this. Any points outside the target will not change shape, and any intersecting will be pulled towards the outside of the target's surface. I'll move the plane 1 meter across in the X direction. Let's set the snap mode to outside surface. I'll also set an offset factor to 0.5 meters. Now, when we move the plane along the z-axis, we can clearly see how the vertices snap to a point around the surface, but it is always set at a constant offset of 0.5 meters. Above surface may seem just like outside surface to begin with, but the difference lies in the direction each vertex is moved towards the target. I'll return the plane to its original position above the sphere. And I'll switch the wrap method to project. We can adjust the snap mode as we could before, but the results are slightly different. For example, inside will project the mesh inside the boundaries of the target, and offset will position the result in relation to the object's face normals. A positive offset will maintain the shape, but a negative offset will change the object back to its original form as it approaches the origin point of the object. The limit is set to 0 by default, which will take into account the full object's surface. If we increase the limit, this will only affect the set radius out from the object's origin along the projected surface. Subdivision levels work a little like an inbuilt subdivision modifier, and it's most noticeable when the limit is 0 and the corners are overly stretched on the target surface. By increasing the subdivision levels, those corner vertices will be projected more accurately. The axis will override normal's direction and instead will project the vertices along the global axes. In this case, the projection has been directed mainly along the z-axis. If we select either x or y, then the direction is combined, and the vertices move along in this fashion. Negative and positive will determine the direction that the projection occurs. This is in relation to the object's own surface normal's direction. I'll tab into Edit mode, and in Viewport Overlays, let's make our vertex normals visible. You can see that they are all pointing away from the target, so this direction is positive. If we only have positive ticked, then no projection occurs because the object's face normals are facing away from the target. I'll undo this step and tick negative. Now you can see that the normals are still pointing away from the target, but the vertices have been projected along the normals in the negative direction. To demonstrate face culling, let's move the plane to a position where the target faces will be both in front and behind the target in relation to the object's face normals. We'll select negative as the direction in which the vertices are wrapped. With face culling off, all the vertices pointing away are wrapped. If I switch this to cull all front-facing vertices, we can see the effect. If I choose to cull the back-facing vertices, back will do a similar thing to inside snap mode, because the back-facing vertices are what are culled from the wrap. But when I click on invert, then this occurs. I'll reset the project settings to their defaults. Now I'll duplicate the sphere, offset it, and scale it a little. I'll then set this second sphere as an auxiliary target. This will allow you to wrap the object by projecting it onto two targets. It can sometimes come in handy, but it will also come with its own set of issues that you should be aware of. You can see how, by scaling and positioning the plane, we can get a wrap which covers both targets fairly well. Let's switch the wrap method to nearest vertex. If our sphere has a subdivision modifier added to it, then the result becomes smoother, as there are more vertices to wrap the object's vertices to. Let's switch the wrap method to target normal project. This will wrap the object's vertices to the target's own normals. And finally, as with a lot of other modifiers, you can just wrap a selected vertex group to the target, or the inverse selection of that group. This default cube already has a subsurface modifier added to it. It is set to simple, and the levels have been bumped up a couple of times so we have enough generated topology to see this next modifier in action. Let's go to our modifier properties, and from the deform list, let's add the simple deform modifier. I've intentionally left shading set to flat, so we can get a clearer picture of the deformation across the mesh. And the default settings will show you immediately how the modifier works. There are 4 modes, and each has slightly different controls. We'll begin with twist. By default, the angle is set to 45 degrees, and the axis it is twisting the object around is set to X. The angle can be increased or decreased between 360 degrees and negative 360 degrees. You can change which axis to twist the object around, And if we add an empty object, we can use this to control where the object twists from. I'll open up the restrictions settings. I'll also edit the width of this cube along the x-axis and increase the levels of subdivision. We can apply lower and upper limits for this modifier. The first limit is measured from the lowest index face, and the second from the highest. I've made these indices viewable for clarity. The range for each spans from 0 to 1. What the limits do is set a hard limit for the modifier to stop working across a given axis. However, increasing the lower limit over the higher limit won't flip the effect. Now currently, the object is using this empty to control its point of origin. That means that the angle of deformation and the local axis are going to be affected by the position, scale, and rotation of this empty. Let's disable the origin and, in object mode, rotate this cube around the y-axis. You can now see that the twist is constrained to the cube's own local coordinates. If I rotate or move this cube in object mode, the twist remains locked to its local x-axis. I'll reassign the empty as its point of origin so that you can see that moving, rotating, or scaling this empty will affect how the modifier is applied. I'll return the limits to their defaults. And while this cube is twisted around the z-axis, let's toggle into top view so we can clearly see how locking the deform on an axis affects the results. The two axes available will always be the two that are not selected as the deform axis. You can see that the entire cross-section of the cube has been twisted. But if I lock X, everything parallel to the x-axis does not deform. Let's subdivide the mesh along its longest dimension and assign some vertices to a group. Let's make it interesting and assign two different areas to the same group. I'll make sure both modifiers can be seen in edit mode. And as I increase or decrease the angle, you can see how the modifier twists only those groups. But the area between the selected groups and the not selected group is what is twisted. We can also invert the effect so that the group remains unaffected and everything else is twisted. Let's return the object to its original rotation, remove any vertex groups assigned, remove any locks or limits, and switch the setting to bend. Bend has all the settings that twist does except for lock. The angle follows the local axes to bend around. If we take a look at the cube's object properties and enable axes under the viewport display, then toggle X-ray in the viewport, the X, Y, and Z arrows on this widget point in the positive directions. When we set an angle to a positive number, the object is bent in this direction, and a negative angle will bend it in the negative direction. Let's play around with some of these settings so that we can see how to achieve some interesting shapes. I'll set the angle to 180 degrees. I'll set my axis to Z, and I'll restrict the limits to 0.2 and 0.8. I'll also set the origin to the empty. Now when I move the empty along the y-axis, we can see how the position will affect it. Let's switch to taper. Now the lock restriction returns, but the angle setting is replaced by a factor. The factor corresponds to the previous angle value, but it can range from -10 to 10. Finally, we'll set the origin to empty and move the empty along the x-axis. Let's set an arbitrary factor. We'll constrain the axis to x, set some limits, and lock the y-axis. All the settings work as they did for the previous deform modes. However, now the effect is a tapering. I'll reset everything to its defaults once again, and now switch to stretch mode. The settings are identical to taper, but rather than distribute the deform across the length of the object, it moves the points of deformation from the center out to the extremes of the object. Setting the origin to an empty object, you can affect the point from which the object stretches out. And if you place this at one of the extremes, or beyond, you can even achieve a smooth taper. Limits and vertex group restrictions work in much the same way. What I like most about this modifier is that even when you know what the settings do, you can get some pretty interesting results. So playing around with it is definitely something worth taking the time to do. The smooth modifier is a non-destructive way of applying what the smooth function does. We do this by selecting our object, tabbing into edit mode, selecting the vertices we wish to smooth, selecting smooth from the contextual menu, and in the dialog box that appears, we are given some options. These options will include a smoothing factor, which you can set between 0 and 1. Note, however, this is a soft limit. The slider might stop between 0 and 1, but you can type in a factor greater than 1 or even less than 0. Repeat increases the accuracy of the smooth, and you can also lock the smooth to one or more axes. However, this method alters the base mesh. I've got a duplicate cube here, and I'll add the smooth modifier to this cube. Now, the settings appear much similar to the smooth function. We can lock the effect to a combination of axes, such as X and Z, increase and decrease the factor, and set a repeat integer for the smooth. However, this will work over the entire object unless we give it a vertex group to work on. So I'm going to tab into edit mode. I'll mark the corresponding set of vertices and assign them to a new group. I'll tab out of edit mode, and in our smooth modifier, I'll assign the vertex group we just created. Now we have a similar effect to the previous cube. However, we have the option to edit this effect. You can note here that the factor does not have a soft limit when it comes to exceeding a setting between 0 and 1. We can set the factor much higher than 1 or even push it in the negative direction. This could come in handy in cases where you might need this additional range. Smooth corrective is a specific use modifier. This will help you adjust problematic areas caused by previously added modifiers, shape keys, or animation. I've set up a simple armature inside this head mesh. I've created automatic weights and bone groups, and an armature modifier was added in the process. Now you can see the lesson on armature modifiers to get a more in-depth look at how this process is done. I'm going to rotate this bone here to a fairly dramatic pose so that we can get some deformation in the mesh which we would want to correct, such as around the nape of the neck here. We can see some of the vertices are pinching and overlapping, and normally this would not be an ideal situation. Now, if this was simply a pose, we could weight paint this, but if this area is something that is affected by a lot of animation, constantly updating the weights could be very time-consuming. So instead, we can add the smooth corrective modifier to this stack and use the settings here to make easy work of correcting an area like this. Already with its default settings, we can see a small improvement because of where the defaults are set. I'm going to reduce the factor to 0. As we increase the factor, we can see that the overall mesh smooths out in the most problematic areas. And by increasing the number of times that the smooth function is repeated, we can get a smoother and smoother result. The scale is set to a default of 1, and during animation there might be times when you have to increase or decrease this to get a better outcome. The smooth type can be set to simple. Now this algorithm just relaxes the vertices in relation to the distance between all of the vertices, or by length weight. Now this method can appear a bit more accurate, and the way this works is by averaging out all of the lengths between adjacent vertices to calculate the path along which to smooth out the affected topology. Let's create a specific vertex group which just targets the nape of the neck here. We'll select this as the vertex group that the corrective smooth will affect. I'll adjust some of the previous settings to get a more favorable outcome. Now, if we animate these bones, there'll be times in the animation where the corrective smooth will not be needed, and instead could cause slight problems. So we can keyframe these settings along with the animation so that the corrected topology is affected at the right times. The only smooth function will show you what the mesh looks like before any correction is applied. Boundaries are usually open areas of a mesh, and these sometimes can be problematic, and we might not want them to be affected. We'll select Pin Boundaries. Now, when we increase the parameters, the opening at the base of this object will not be affected. By default, Rest Source is set to original coordinates, but it can also take into account bind data from modifiers that might be higher in the stack. There's a lesson on surface deform modifiers for a more in-depth view about this, but for now, I'm just going to add this plane, subdivide it a little. Let's add a surface deform modifier and move this above the corrective smooth to see how this works. Set the neck as the vertex group that will be affected, and then click on Bind. We can now deform the plane, and the coordinates are better represented. So in combination, this modifier gives you lots to consider for a number of situations which might arise. If you want a little more control on what is smoothed, and simple smooth is not enough, then Laplacian smooth will give you some extra options that you might find interesting. I have here a simple lathe. It is spun using the screw modifier. You can learn more about that modifier in the screw modifier lesson. The shape I've created, this wine glass, is basically a cylinder with two open ends. Let's add the Laplacian smooth modifier to the stack. The settings are similar to the simple smooth in that we can set a repeating factor, limit the effect to one or more axes, or isolate the effect to a vertex group. The factor setting has now been replaced by two options, a lambda factor and a lambda border. For you maths nerds, the lambda factor refers to the part of the smoothing algorithm which affects the roughness of the resulting curve. A low lambda value retains much of the detail present, whereas a higher value will average out all of the points to a combined average curve. The next two tick box settings are enabled by default, and they preserve volume and normalize the curve. I'll disable these so we can examine how they affect the overall result as we begin to tweak the other settings. Let's begin with repeat. Each level of repeat accumulates the smooth function. The higher we set this value, the smoother the curve becomes without changing any other options. We can restrict any of the smoothing to one or more axes. Think of adjusting the lambda factor as controlling the smoothness between each of the open borders, and the lambda border as controlling the smoothing only at the open borders on a mesh. When we enable preserve volume, the overall volume as described by the original shape is maintained. The normalized setting will take all of the settings so far and apply a normalize function to distribute that data. Isolating this modifier to a single vertex group is also an option. In short, the Laplacian smooth is like the regular smooth function, but with much more granularity to achieve a more desirable result. I've created this chainmail object using two interconnected rings with a subdivision modifier added, then positioned so that they will overlap correctly when adding an array modifier for both the x and y directions. Now, doing a cloth simulation directly on this object would be difficult, so instead we can add a simpler object like this plane and add a cloth simulation to the plane, provided it's got enough subdivisions and topology to affect our chainmail. Now, this next part of the demonstration is optional for those of you who already know how to set up a cloth modifier, so you can skip ahead. For everyone else, I'll take you through the basic process of adding a cloth modifier and simulation to the plane. We'll select the plane, add the cloth modifier to it. Now, I want this plane to be something like a curtain blowing in a light breeze, so I'll need the top of it pinned. I've created a vertex group, so let's assign this top row of vertices to that vertex group. If we switch over to weight paint mode, we should be able to see the difference in weight very clearly. We'll tab back into object mode, and we'll go into the physics data properties so we can see all of our cloth simulation settings. There are a lot of them, but we're really looking for just one setting here, and that's under this area, labeled shape. Here we can tell the cloth simulation to pin a selected group, so we'll select our pinned group. Now this plane will act just like cloth, but we'll have to add a physics effect so that we can complete the simulation. I'll just hit Shift A and add a wind physics effect and position it in such a way that we can see the direction that the wind will blow. Now, because we're using all default sizes, the default wind setting for strength is really, really low. So we got to give this some decent movement. I'm going to bump this up to maybe about 500. Now, this should be all that is required to get the effect right. So let's play the simulation and watch the plane as it deforms like a curtain. So let's bring back our chainmail, select it, and add the surface deform modifier to it. Now this will sit at the bottom of any other modifiers that we've added. I'll select the plane as the deforming object. We've got to make sure we're on frame 1, click on bind, and play through the animation. Now you can see how the chainmail waves just like the plane, even though it's got all those other modifiers added to it in the stack above the surface deform. Now let's look at the settings for the surface deform modifier in a little bit more detail. Without unbinding the modifier, we can change by how much the object is affected by the surface deformation. By default, it's set to 1, which means it's going to correspond almost exactly to the target. If we lower this towards 0, we can dampen that effect until there's no effect at all. You do have the option to increase or decrease this strength dramatically over 1 and below 0 should you require it, but in most cases this is going to give you some very unexpected results. Now I've made a duplicate of this entire setup here, but in this one I've applied the array modifiers to the chainmail, so the only thing that we've got is the subsurface for the rings and the surface deform so that it can deform with the plane. I've created a vertex group to demonstrate that even when the mesh has been bound to the surface deform modifier, you can still select a vertex group to affect, or affect the inverse of this group. Let's unbind this for the moment and select a group before we bind the mesh. We have this option called sparse bind. This means that the group will have to be selected before the binding process. If we bind and then try to change the vertex group, that vertex group will not have an effect. Now finally, we've got this interpolation fall-off, and this controls how smooth the deformation appears. Now it can be set between 2 and 16, obviously 16 being the smoothest, but in a case like this, the lower setting can actually have the more desirable effect, as setting the fall-off too high can create artifacting. Ironically, it's because of how accurate the mesh will follow the target. Now we've got these nice big chunky rings, and we want to see them moving as if they were rings, not as if they were made of cloth. So I'm going to set that back to 4, and let's just play through that animation. The warp modifier will push vertices away from one selected object in the direction of a second selected object. Here, I have a plane. I've subdivided it a couple of times and then added a subdivision modifier to it, set to simple, so that we can get a reasonable amount of topology to work with. I'll add an empty and set it as a single arrow. This will be the object we warp from, and I'm going to leave this at the same coordinate as the plane. I'll add another empty, but this one can be the regular 3-axis shape, and position it a little above the plane. Now selecting the plane, we'll add the warp modifier to it. We'll select the object from and to, and the effect is immediately obvious. Before we adjust the settings, let's move the empty objects around and see how they affect the plane. I've labeled the arrow empty origin. Notice how it affects the mesh if I move it above or below the plane. Now let's do the opposite and move and rotate the empty that I've called target. Now that we have some interesting positioning, let's take a look at the modifier settings. I'll select the plane once again. Because we rotated the target empty, the mesh will stretch and lose volume along the way. We can click on Preserve Volume, and the warp won't appear as stretched. The strength control will allow us to reduce or increase the warp as a factor. Now, obviously, when set to 0, the factor is nothing, and 1 typically stretches all the vertices to the point of the target. But you can increase the strength considerably and have the mesh warp far beyond the target, or even away from it. I'll make a random selection of vertices and assign them to a group. Now we can use that group, or its inverse, to isolate what parts of the mesh are affected by this modifier. The fall-off setting will allow you to select the type of fall-off curve. You can also control the radius over which the fall-off curve is distributed. We can even use a texture to determine the pattern of the warp. Let's add something random, like the magic texture, and mess about with some of the settings. We we may have to increase the subdivision surface modifier a bit in order to get a smoother results. Now the texture coordinates can be set to local, global, object, or even UV. I'm going to set it to object. And I'm going to use the target empty as the object. Now, by adjusting the settings on this modifier, we can get some really interesting results. Like some other deform modifiers, the wave modifier will require adequate topology and enough surface area to achieve best results. I've modelled this hemisphere, and it's about 20 meters in diameter, with plenty of subdivisions. Let's select it and add the wave modifier to it. Now, without changing any defaults, if I hit the spacebar, we'll see how the waves emanate from the center of the object and then affect the entire object. I'll pause the animation partway so we can examine the settings more closely. First up, we have motion, and we have two settings, X and Y. When both are enabled, the waves form concentric rings because they're propagating in both the X and Y axes. However, the waves can be restricted to just move along the X or Y axes. I'll enable both so we can get back our concentric rings. By default, cyclic is enabled. If we disable this, the wave will animate once and then it will stop. Just like the motion can be restricted to X or Y, we can also restrict the movement to the object's own normals in the X, Y, and Z directions. Next, we have some settings for determining the wave's height, width, and narrowness. We can play around with each slider and achieve sharper peaks, more widely spaced waves, or even wider waves. We can even push the factors in negative directions. We can isolate the effect to a single vertex group. I've already created two and assigned vertices to a surface group and a hemisphere group. I'll select surface. Now when I hit the spacebar, only the flat side of the hemisphere has waves on it. Inverting the selection just causes the modifier to be applied to everywhere except that vertex group. Fall-off controls the distance from the center of the wave over which the effect will fade away. Now the center of the wave can also be offset. We can adjust the start position by offsetting the center in X and Y directions, or even add an object such as this empty. If we play the animation and move the empty around, we can dynamically change where the wave's center is, even while it is animating. Now let's take a look at some timing controls. Here, we can offset the wave effect in numbers of frames and even fractions of a frame. At 0, the animation will begin at the start of the timeline. If we offset it by a positive number, the wave will be delayed by that many frames. And if you offset it by a negative number, the wave is assumed to have already been in motion that number of frames, and the effect will begin part way. You can also set the number of frames that the wave will animate over. Now this can work well in conjunction with the damping slider. So let's say we give the wave a lifespan of 5 frames, but that it dampens out over 10. Now we'll get a smooth transition from the start of the wave to where the surface settles once more. The speed of the wave can be variable and is measured in the number of frames that a ripple takes to form. You can also set the speed to negative values, but to see this in action, we'll have to set an offset positive 100 and then set the speed to negative 0.025. Now the animation shows the ripples moving towards the keyframe that we've offset it to, as if in reverse. The texture settings allow you to add a texture much like you would with a sculpting brush. When the wave modifier animates, the texture will distort the surface normals in one of four ways. Global, local, and UV will map the texture according to those coordinate systems. But if we use object, then the texture is mapped according to the origin point of a chosen object. You can dynamically change where the texture is offset by moving the object around even while the waves are animating.